and BC. So let's call that omega AB, omega BC. At the instant when theta is 30 degrees. Also sketch the position of the link BC when theta is 50, 45, 30. Let's just skip that part. I'll post a solution for everything, but let's skip that for now because I need to do quite a few questions. Okay, so a problem like this can be done in two ways. One way is using purely the equations of relative velocity of points A and B and B and C, write the vector equations and solve for the unknowns. The other way is to use instantaneous center of zero velocity. Okay, what I would do is let me solve this using IC. By the way, I will have a question on IC, and I'll also post how to do this problem using vectors, okay, relative velocity formula. So I'll post the solution to this problem using vectors, but I will solve it in the class using IC. Okay, so what I'll do is I'll try to find the IC of link BC. The IC of link AB is, what's the IC of link AB? IC is the instantaneous center of zero velocity. So it's at A. So the point at which is at zero velocity is called the IC. So for link AB, the point A is at zero velocity. So that's the IC. For BC, that's less obvious because C is moving. B is also going to turn, right? It's going to go in circles about A. So B is not at zero speed. C is not at zero speed. We need to find the point which is at zero speed. So the procedure is as follows. Okay, find 2 points whose velocity direction is known. In this case, we know the direction of velocity of C. It's vertical because of the groove. We know the velocity direction of point B because AB is moving in circles. The point B has to have a velocity which is at right angles to the link AB. Okay, so once we draw the direction of velocities of the 2 points, we draw normals to those 2 points. So normals to the velocity direction. So in this case, the normal to the velocity vector along C is going to be in this direction, 90 degrees. And the normal to AB is this way. Which is again 90 degrees, and that point of intersection of the two normals is the IC. Okay, it's a very simple procedure. People forget to do this. It's easy points if you know how to draw the IC. In the exam, if he asks you to draw the IC, you do not have to draw a separate figure. Just draw the IC on the figure itself, whichever we've given to you, so that you save space. And if you do not ask you for distances, you do not have to compute distances. Like you do not have to find this distance or this distance, unless, of course, you're using that to solve the problem. In this case, I'm going to solve the problem using the IC distances. So I'm going to figure that out using geometry. Okay, so the next thing is we got to find, well, that's the formula for the velocity, and that will motivate us to find what are the lengths we need to find out. So velocity of B is, okay, first of all, A is the IC, right? So this is the velocity of A is 0. So if you look at link AB, then we can say that velocity of B is the angular velocity of AB times the distance of B from A, right? Or in other words, if you like to think of it in terms of IC, then A is the IC, and so you can write that formula down for link AB.
I have a question.
Yeah.
When will we need to do cross products? When will we not have to do cross products? Is it when we're using IC, we don't have to worry about it?
So the question is, when do you have to do cross product? When would I write this as VB equals omega cross RB with respect to A? And when would I write it this way? When you're absolutely right. When you're trying to use ICs, you do not have to write the vector equations. When you're using the formula to solve this problem, so there's another way to do it, which I'll post by the way. You'll have to use the cross product. So, question, yeah?
What about when you're using like a problem, let's say I have a bunch of links and you're using both methods? So on the link where you're using IC, then you just use the magnitude. But on the links that you're using like the other method, and you use indicator, and you just
yeah. So the question is, what if you want to mix two ideas? Like in this case, you could potentially use the IC for AB, but not use the IC for link BC. Whenever you switch from IC to non-IC method, non-IC use vectors. IC don't use vectors. Okay. I would recommend that you use one of the two. My personal preference is IC because it's intuitive and easy. If you're more inclined to writing equations down, you're comfortable with cross product, do it with vector equations, and you have to equate the I and j components. But we would never, at least I would never ask you a question where I would say, solve this using the IC. I will say, just solve for the velocity. But I might ask you a question, draw the IC, in which case you have to draw the IC, but you do not have to use the IC formulas to solve the problem. Okay, so you can choose which one you want to use to solve the problem in the exam. So velocity of B is unknown. Omega AB is unknown, and the length of AB is, you can see it's 1 feet. Okay, so there are two unknowns. We can't solve for the two unknowns unless we generate more equations. So this is where we go from AB to BC. So let's write the equations for link BC, and this is where I'll use the IC. So velocity of C, let me write it this way, omega BC equals velocity of C divided by the distance of C from the IC. And when I say the IC, it's the IC of link BC, it's not the IC of link AB. Equals velocity of B divided by R P divided by IC. Okay, omega BC is unknown. Velocity of C is given, it's 6 feet. This is something which I think we can find from trig. So also RB with respect to IC, and velocity of B is unknown. So what I'm going to try to do is find this distance and this distance using trig. Once I have those distances, I will be able to solve for omega BC and VB, and then I'll use VB to solve for omega AB. Okay, so in this case the hardest part is, besides finding the IC, is to find these links, but that's really trigonometry. So let's try to find this distance RCIC and RP. RBIC, which is the distance from B to this point, okay, not to the point A. Yeah. Question? Okay, if you like, you can draw this figure again. Sometimes it makes it easy. Let's see what we know. We know this is 3 feet. This is C, this is B. Okay, now is this 90 degrees? It is 90 degrees. Because AB is, that's because AB is vertical as it's shown, and C is also vertical, so the normal is at right angles, so this has to be 90 degrees. Okay, so we need to find this distance and this one, RBIC. And here's the thing about a triangle, which is if you want to find sides or angles of a triangle, you need to know 3 pieces of information. You need to know either 2 angles, one side, or 2 sides and an angle, and so on. So in this case, I know one side, it's 3 meters, the and I know this angle is 90 degrees. I need one more piece of information to solve for slope. What else do I know? 30 degrees, right? So I know that this angle is 30. So this angle has to be 60. This is 30. So this angle has to be 30. So RCIC, you can see, is 3 cosine 30. And RBIC is 3, if you like, sine 30, which is 1.5, and 3 cosine 30. .6 feet. Okay, so now we are all set to write this equation down with whatever we know. Omega BC is unknown, velocity of C is 6, RCIC is 2.6, VB is unknown, and RBIC is, we just found it's 1.5. So omega BC is 6 divided by 2.6. It's 2.31. VB is going to be 2.31 times 1.5. 3.46. So that's radians per second, feet per second, and then we can put this VB in this equation here, the first equation I wrote, and find omega AB. So VB is 3.46 equals omega AB, which is unknown, times the vector from A to B, the length, so it's 1, and so omega AB is 3.46 radians per second. So we were asked to solve for omega AB, that's the answer, and then we were asked to solve for omega BC. Okay, now one thing is, if you're told to find the direction of the angular speed, how do you do that? With vector equations, the vector will tell you the sign, positive or negative, but with scalars like this, you do not quite see how do you find the direction of the angular speed. Well, it's actually pretty simple to think about it. So point. So if I want to find the direction in addition to the magnitude, this is how I would proceed. So C is the point of zero speed, and it's as if the C moves up, and C is the point, IC is the point of zero speed. So if it's almost like C is pinned about point IC. And so if it's pinned about IC, which is at zero speed, and if velocity of C is upwards, then BC is going to go counterclockwise, because this whole thing, think of like a big rigid body which encompasses think of a rigid body which encompasses CB, but it is pin jointed at IC, because what is IC? It's the point of zero speed. So think of BC as a rigid body. Everything is pinned at IC. At this instant, by the way, that IC will change as things move. If everything is spinning, then BC is going to have a counterclockwise speed because C is going upwards. So this is going to move counterclockwise, which means this is going to move counterclockwise. So omega BC is counterclockwise. And we can use the same logic for B. Okay, if BC is moving counterclockwise, VB has to move to the left, which means AB has to be counterclockwise.
Is that ratio always, when you're using the IC, is it always true? Like the WBC, DCR, that's always true?
Yeah, this is always true. Okay, any questions on this?
So just to confirm, that ratio is always true. Like omega BC is always, that's the formula to memorize.
That's the IC formula, absolutely.
Okay. All of that right there, that's always true.
That's always true.
Okay.
So I'll post this. This is the solution from the book. The book does not use the IC to solve it. They actually use the relative velocity formula, and they get the same answer, counterclockwise, 2.31, 3.46. Okay, I'll post this, but you are not constrained to use IC. You can use this method if you're more comfortable with using vectors. Okay, so I think the next problem which I think is important is this one, because after I post, this should be divided by 2. I've had people struggling with this problem when I gave it in the exam. Okay, 2 blocks A and B have mass 5 kilogram and 10 kilogram. So 5, yeah, 10 kilogram. If the pulley can be treated as a disk of mass 3 kg and radius of 0.15, determine the acceleration of block A. Neglect the mass of the cord and any slipping on the pulley. So we want to find the acceleration of block A. Okay, so intuitively, if 10 kg, well, B is heavier than A, B has to move downwards, A will move upwards, and so we can, it's fine to assume a direction like this. So here's an important difference between particles and rigid bodies. The acceleration of B is not the same as the acceleration of A. If the same question was from the previous, the chapter 30, where the pulley had no mass, then acceleration of B would be equal to the acceleration of A. But because the pulley has mass, that is simply not true. In fact, the tensions in the cable on the left and right are not the same. So for particles, they are the same tension. And you can actually reason it out. You can actually write the equations for this, assume that they're not equal, and then when you try to put the mass of the pulley equal to 0, you'll actually find that it simplifies to acceleration of A is equal to acceleration of B, and the tension on the left side, that is tension in A, is equal to the tension in B. So it's very important that you distinguish that, because that will affect your answers. Now, clearly, in this case, if you ask for acceleration, this is not a problem from chapter 16, which is on kinematics. It's a problem on dynamics because you're given masses and so on. Okay, so first thing is, if you identify it's a problem in dynamics, there's always some credit given to free body diagrams. Try to draw free body diagram. In this case, we have multiple choices. We can draw free body diagrams for A, for B, for the pulley. And we can also draw a free body diagram for the entire system of pulley and the masses. And actually, there are the advantages of using one or the other. Let me just draw the free body diagrams first. So, and just feel free to draw multiple free body diagrams. That's fine if that helps you to solve the problem better. So here are multiple free body diagrams that you can draw. Draw a free body diagram for A. Can draw a free body diagram for the pulley only. So that's going to be TA, TB. And then the tension up is going to be, you could write a different variable, or it's simply TA plus TB. No, it's not TA. Let's call that T. And then there is mass of the pulley. Let me call that MPG. And then draw a free body diagram for B. It's tension upping upwards, and then there's MPG. Okay, so I drew 3 free body diagrams. That's the first instinct, right? To draw 3 free body diagrams and try to write equations for all the 3 free body diagrams and solve the problem. Now, the issue with that is it's not. You can use this way to solve for the acceleration of waves. However, what happens is when you try to solve for this system, you'll have to write equations for A, right? It'll be basically F equals ma in the y direction. You have to write F equals ma for B in the y direction. You'll have to write F equals ma in the y direction for the pulley, and you'll also have to use a moment equation, moment about the center point O. And so you'll be writing down 4 equations, and in those 4 equations will help you to solve for A, AB, AAB, and tension TA, TB, and of course capital T. But you are not quite interested in solving for TA, TB, and so on. If I did ask you to solve for TA and TB, you'll be stuck with drawing this free body diagram and solving for TA and TB. But since I've not asked you to solve for TA and TB, try to minimize, in order to minimize the number of unknowns, you're better off not drawing multiple free body diagrams. What I would do is I would draw one free body diagram for the entire system, and it'll be clear why I'm doing that in just a bit. So here is another free body diagram. It's okay to keep them. If you draw this free body diagrams, do not erase it, because you can get partial credit if you missed on something else. So let's draw one free body diagram for the whole system. Okay, so by drawing that free body diagram, we've effectively eliminated 2 tensions, the TA and TB. Okay, so when we do Newton's laws for a rigid body, there are 3 equations, right? Fx, Fy, and moment equation. There's no dynamics in the x direction, so we ignore that. We can write equation in the y direction, F equals ma in the y direction, but the issue is that will only help us to solve for t, capital T, this one. And we are not interested in solving for capital T, so let's try to avoid that, avoid writing that equation. Let's just try to write an equation so that we eliminate T from our equation. And one way to do it is to take moment about that point O. If you take moment about O, capital T will not appear in the equations because the force T passes through O. Okay, so a better strategy is to take moment about O equals. Now, when you take moment, if you look back through your notes, there are basically three things. One is it translating? Is it rotating about an axis, or it's translating and rotating? Right. The 3 sections we did. Translation is when things are only moving in back and forth; they are not rotating. It's clearly here the pulley is rotating and the masses A and B are translating. Right. So you'll have to think of this in terms of general planar motion, which is the formula for that, if you look through the notes, is it's MO equals I G alpha. In this case, I'll write it as IO alpha because the center is at O, G is O, plus R cross MA, right? So in this case, since the two translating objects are A and B, I would write cross MAA plus R P with respect to O cross MAB. So in other words, if you go to section 17.5, that's the section general planar motion where we talked about rolling disk. That was the formula, translation and rotation. So we'll expand this out and see if we can use this equation to solve for acceleration of A. So the moment about O, well, from the free body diagram, we can see that there are four forces. There's capital T, there's MPG, but both those forces pass through O, so they do not have any contribution. So the two forces that are left are MAG and MBG. So let's write the moment due to MA and MBG. We move things a little bit around so it's on one line. Yeah.
Is that the mass of the whole system or the mass of A and the mass of B?
Good point. That should be mass of A and B. Good catch. It should be mass of A and mass of B. Because it's only A and B which are translating and not O or the pulley. So moment about O, we have MAG and MBG which are contributing to the moments. MA times G. To take the moments about point O, we need the moment arm, which is the radius of the pulley, which is given as 0.015. I'll write it as R first. And then you're going to see what if the torque or the moment is clock or counterclockwise. So if you hold the pulley at O and if this force is applied this way, it will cause a counterclockwise torque this way. And so if it's counterclockwise, then the sign is positive. So I'll put a positive sign. And then due to MBG, it is going to be mass times gravity times, again, the moment arm, which is R. And again, hold the pulley at O. The force B is to the right, so it will cause a clockwise torque or moment. So I'll put a negative sign. So that's all which is there in the left side because two forces didn't contribute to the moment. The inertia about the center of mass O is mass times, so it's going to be mass of the pulley now, radius squared times alpha. Now, if we choose alpha counterclockwise, then I would put positive alpha. You have a choice here. If you want to rather put, we know that if A goes up and B goes down, then the pulley is going to turn counterclockwise, right? Sorry, clockwise. So if you assume it to be clockwise, minus shouldn't be there, then you need to put minus alpha.
So is it over 2, like it says on the paper, for MR squared?
The inertia.
Yeah, good. It's mr squared. So inertia for disk is half mr squared. Yeah, question?
So MAG R is positive? Like it's
MAGR is positive, right? Because if you take the disk and if you apply moment, so
oh, your swing is going down? Oh, yeah, of course. Okay.
No, MAG
Yeah.
is down because it's MG. It's not this. That is counterclockwise. Sorry. Okay, so again, this is very important. If you choose it to be clockwise like I have, you put minus because clockwise is negative. If you have chosen it to be counterclockwise, I would put plus. Okay, that will be consistent. Okay, now let's find this. Now there are two ways to do it. One is you find the vector from O to A and cross it with MAA, or you can do it intuitively without having to write the vector product. I like the intuitive way. It's really very simple. This is how you do it. I'm going to write this over here. I'm going to write the magnitude, which is really simple. It's simply MA, acceleration of A, times the moment arm from O all the way to A, which is simply R. What's missing is the sign. Is it positive or it's negative? So the way to do this is MA, think of that like a force, and since acceleration is upwards, that force is upwards. We need to take the moments of that force about the point O. Okay, so it's going to cause a clockwise moment, and so I've put a negative sign. So again, think of this mass times acceleration as a force. Think of this as a force. That force is upwards because A is moving upwards. About point O, that force is going to create a clockwise star, so put a negative star. We can do the same thing with B. MB, AB times the moment arm, which is the distance from B to this point to center, which is R. Again, same logic. If MB times AB is a force, that force is downwards because acceleration of B is downwards. So if that force is downwards, if we take moment about O, it's going to cause a clockwise torque, and so one moment, so it's negative. Here again, AB is downwards, so this force is downwards. About O, it's going to cause a clockwise torque, so negative.
It's turning the same way. The accelerations are equal, right?
No, not equal, no. If the pulley was massless, they would be equal. If the pulley is not massless, it will not be equal. Okay, so everything here is known except for alpha is not known, AA is not known, and AB. Everything else is known. You're given mass, gravity, radius, and so on. Okay, so we need to, in this case, it's one equation and three unknowns, alpha, AA, and AB. So let's just write this as one. We need to generate two more equations to solve this problem. And the two equations actually come from kinematics. There is a specific relation between acceleration of point A, or acceleration of this, or the acceleration of this point, and the angular acceleration. So if this point A does not slip, that's our assumption, it's going to unwind from the pulley. It's almost like a rolling disk. The acceleration of A is going to be alpha times R, because this point A, no slip. And same for this point B. So that's my equation 2. And AB is alpha times R, so that's equation 3. And so effectively, those three equations help me solve, allow me to solve for first alpha. So what I would do is I would take AA, shove it in here, AB, put it in there, solve for alpha. Once I get alpha, it's easy to solve for AA or AB. So AA is asked, and you can.
I thought you said AA wasn't equal to AB.
A is not equal to AB, but in this case it is. Yes.
Okay.
So here's how you can be tricked. This is a very common way in which you can trick people in the exam. What they do is they take this link and they put it on the inner pulley.
Okay.
When you put
Because that's the
inner,
same radius. That's why.
when you put in the inner pulley, what happens is, because of that relation, it becomes alpha times the inner radius, alpha times the outer radius, and they don't become equal.
Okay.
So yeah, just be careful. Don't assume anything unless it's given. So be careful about the figure which is given. Okay, so from 1, 2, and 3. You can solve for accelerations, all accelerations in fact. It's 2.97 meters per second square. Yeah, so in a way I was mistaken. It's not really the pulley mass which determines if they're equal or not. It's the radius of the pulley, not the pulley mass. But the tensions, TA and TB, actually depend on the mass of the pulley. So accelerations depend on the radii of the pulley, but the tensions, you can check this calculation, TA will not be equal to TB, and that the reason is because of the mass of the pulley, not because of the kinematics. Okay, is that clear? Any questions? Yeah.
In your drawing and in the equation, can you tell me what the reference was and tell me and denote both clockwise and clockwise and equation 1?
For equation 1, the reference for any particular part or?
Yeah, when you were telling us which way was clockwise and which way was counterclockwise.
Sure, yeah. So this is an equation which involves taking moments about point O. So if you see that the force is causing a clockwise moment about O, it's negative. If it's causing a counterclockwise torque, it's positive. That's all. And so that's true for each and everything here. Each of these things would come from looking at the pulley with reference at O. Assuming O is fixed, it's not rotating, O is a fixed point, and things are rotating about point O. Okay, any other questions? Yeah.
Not for this question, but like if I know there was one where like a dump truck has an acceleration, it's moving, and you end up doing something similar to this. You would take moments on the left side versus moments on the right. I remember in that problem on the right side of the equal sign when they were calculating negative moments or whatever, they set it negative. Is there a reason you always do that? And also, when they're doing a moment, do they only take the x component of that moment on that side, or is it depending on your plane of motion?
Was it a problem involving? Is that a homework question?
It's one of the homework questions. Yeah, the dump truck one I'm talking about.
Do you have it printed?
I do.
Okay, the smooth 180 lb pipe has a length of 20 feet and negligible diameter. It is carried on a truck. As shown, if the truck accelerates at 5 feet per second square, determine the normal reaction at A and the horizontal and vertical components of forces which the truck exerts on the pipe at B. Reactions at A and reactions at B. I think is it pin jointed at B? Like that, yeah. Doesn't say that, okay.
So that's why I just assumed it was normal, but then that's why you're wrong.
Okay, so first of all, there are going to be how many unknowns? I think there are going to be two unknowns at B, like they've drawn the figure, and then at A, there's going to be a reaction force. And I think that's going to be at right angles to A. Okay, so the question is it the last part, this one?
Yeah, the last part. So on the right side of the equation, right?
Okay, why do you get negative?
Is that because I see down there where they do the free bodies, they translate it from stationary to moving.
Let me zoom that. So question is, why is this negative? So the reason I think is mass times acceleration. This is ma.
And that's going to cause a clockwise.
Yeah, and you take moments about point b. This is b,
Okay.
and so that goes the clockwise.
Okay. So we always take our acceleration of our object and move it with how everything's progressing.
Yes, think of the mass times acceleration like a force,
Okay, yeah.
and that force is called the clockwise.
Thank you very much.
Okay, so we have 9 minutes. So, I mean, something like this, I would not give you a question like this in the exam, but maybe in the finals. And this is not hard, but I wouldn't quite give it in the first exam. So let me skip this. I'll come back to this. You won't have this question in the exam, pretty much. I can tell you that. But I might have this question in the finals. Let's skip this because, in the interest of time, let's skip this. I'll post a solution, but remember to go through this question for the finals, and I'll try to do this in the finals. Let's do the other two problems. I think they are more important than this one. For example, this problem. Okay, if omega is 2 radians per second and theta is 30 degrees, find the magnitude of velocity of mass b . Okay, so first thing to note is that you're not given the mass, the value of the mass of B, right? You're not given the mass. And so since you're not given the mass, that's a hint that this is not a problem involving dynamics. It's actually a kinematics problem. So you do not have to use Newton's laws. Okay, so we need to find the velocity of B. If this thing turns counterclockwise, then B is going to clearly move up. So what's going to happen is, just this down. So the point A is actually as let's call this point O. As OA rotates and the length OA remains the same, right? It won't change. But as OA rotates, the length AC is going to stretch, right? It's going to pull up some length of the cable from CB, and so AC is going to grow in length equal to the amount BC is going to shrink. That convincing? So the distance BC shrinks is equal to the amount of distance AC stretches. So velocity of B is essentially the rate of change at which AC is stretching. So it's a 1:1 relation. So what I'm trying to say is that if you can find how fast, if you can find, let's say that this is x, which is, let's call that xac, then what I'm trying to say is that the rate of change of xac or dxac dt is the same as velocity of b. Okay, so it's very important that you do that first. Otherwise, you cannot solve it. You have to understand conceptually that the length at which AC stretch is equal to the same length which is shortened from BC. So what we got to do is somehow find xac and then differentiate with respect to time. Okay, so how can we relate xac to things we know about? We know the different lengths, and we know theta.
What was the answer? Can you just tell me the answer?
The final answer is 0.47. Okay, so you can use, somebody said cosine rule. So this is known. The 3 feet is not going to change because that's the length, the radius of the disk. The length OC will not change, that's 5. And this is theta. So XAC equals square equals 3 square plus 5 square minus 2 times 3 times 5 times cosine of the angle between 3 and 5, which is theta. So you could, there are a number of ways you can take the derivative. One way is you write this as XAC equals square root of something. But the other way to do it is to just differentiate the expression like the way I've written it right here. So in this case, it will be 2XAC times XAC dot equals derivative of 3 is 0, 5 is 0, minus 2, 3, and 5, they remain as it is. The derivative of cosine theta is minus sine theta, and derivative of theta is theta dot. And so XAC dot equals, cancel off the 2, sine theta, theta dot divided by XAC. Okay, so theta is 30 degrees, theta dot is omega, which is 2. We need to find XAC, but that's simply 3 square plus 5 square minus 2 times 3 times 5 times cosine of 30 degrees.
Shouldn't it be 15? Theta dot?
Well, it's 2 times 3 times 5.
Should be, yeah, it's 15, isn't it? I think this is right.
No, but like you didn't carry it down.
Yeah.
Didn't I carry it down? Oh, yeah, this should be 15, my bad. Absolutely. Absolutely, yeah. So, where the 2 cancelled with this 2 on the left side. Okay, so this is XAC is known because I put in sub in the value. So you can put XAC theta, theta dot in that expression, and X dot AC is 0.47. Okay, let me give you credit for attending. I did not have any questions, but you can poll any answer you want. It's going to be multiple choice, but click A, B, C, whatever you want. I'll just.
So theta dot equals omega.
Theta dot equals omega is. Yeah, is omega, right? Because the rate of change. Do you have any questions about the exam?
Will you give us mass movement inertia?
Give what?
Mass movement inertia?
Yeah, so we do not expect you to remember mass movement of inertia. I'll give that to you. Anything else?
It's going to be the same stuff as last time, where
Yes.
the problems are going to come from practice, exam, review, and homework.
No, what? So for sure, one question is going to be from the problem I did in class, similar to that. But other 2 questions, there are only so many things, so I'm not